All right, let's jump right in. This deep dive, tailored just for you. We're tackling circles today, pulling insights, directly from the chapter you sent over.
Yeah, absolutely. Our goal isn't just like listing definitions. We want to pull out the core ideas and really get into the fascinating bits about this shape, give you a clear path to understanding it.
Exactly, because circles, well, they pop up everywhere, don't they? Tiny things, huge buildings, and they're kind of fundamental. So let's see what makes them tick.
Well, at its heart, a circle is actually incredibly simple. The material defines it as the path a point makes. If it stays always the exact same distance from one fixed point.
Okay, and that fixed point, that's the center.
That's the center.
And the fixed distance, that's the radius.
Precisely.
Sort of like using a compass. The point stays put, that's the center, and the pencil draws at that fixed radius distance.
Exactly like a compass. And the whole path it draws, the boundary line, that's the circumference, basically the circle's perimeter.
Got it. Okay, so moving inside, lines within the circle, they have names. Any line segment connecting 2 points on that circumference, that's a chord.
It's a chord, yes. Any 2 points on the edge, connect them straight across. But there's a really important chord, the diameter.
Ah, right. That's the one that goes through the center.
Exactly. It has to pass through the center. And it's always the longest chord you can possibly draw in a circle, always twice the radius. The source material actually gives a good example. Like, you can't fit a 20-centimeter chord in a circle if its diameter is only 16 centimeters. It just won't fit.
Right. Physically impossible.
Makes sense.
Okay, and what about, like, position? Inside versus outside?
Simple idea. Really crucial, though. It all depends on the distance from the center compared to the radius. If a point is closer to the center than the radius length, it's in the interior.
Inside the circle.
Inside. If it's farther away than the radius, it's in the exterior.
Outside.
Outside. And if it's exactly the radius distance away...
Around the circle.
On the circumference. Yep. The material uses numbers, like for a 12-centimeter radius. 9 centimeters is inside, 12 centimeters is on, 18 centimeters is outside. Clear examples.
Very clear. Okay, parts of the circle itself. Like pieces of the boundary.
Right. So a piece of the circumference is called an arc.
Just a segment of the curve.
Exactly. Could be a small piece, a minor arc, or a really big piece, a major arc. Or if a diameter cuts the circle perfectly in half, each arc is a semicircle.
Half the circle makes sense.
And then there are like slices within the circle area. A sector is like a pizza slice, bounded by 2 radii.
And the arc between them.
And the arc between them, yep. Then a segment, that's different. It's the area cut off by a chord.
So the chord and the arc it creates.
The region between that chord and its arc, yes.
And there's an angle involved too, the central angle.
Ah, yeah. That's the angle formed right at the center of the circle, usually by the 2 radii that define an arc or a sector.
Okay, got it. Now, what about lines that just touch the circle from the outside?
Right. This is where some really neat geometry comes in. We're talking about tangents.
Tangents. The material says it's a line that hits the circle at exactly one single point.
Precisely one point. That's called the point of contact or point of tangency. And here's the really key thing, the big insight from the source. That tangent line is always perpendicular to the radius drawn to that exact point of contact.
Always a 90-degree angle.
Yep.
Right there where it touches.
Always. A perfect right angle. Every single time.
Wow, okay. That seems useful.
Oh, it's incredibly useful. That's why, like the material shows, you often use the Pythagorean theorem in problems involving tangents, because you've instantly got a right angle triangle formed by the radius, the tangent segment, and the line from the center to the external point.
Ah, I see. And the source also mentioned drawing 2 tangents.
Yeah, from any single point outside the circle, you can always draw exactly 2 lines that are tangent to the circle. And interestingly, the lengths of those 2 tangent segments from the external point to where they touch the circle, they're always equal.
Huh. Equal lengths. Okay.
One last really special angle to cover, this one inside the circle, the angle in a semicircle.
Angle in a semicircle. Yeah. Okay, how's that formed?
You take the 2 ends of any diameter.
Okay.
And you connect both of them to any single point you choose on the circumference, on the arc of the semicircle.
So it forms a triangle using the diameter as one side.
Exactly. And the amazing thing, the absolute rule highlighted in the source is that angle you just formed at the circumference, it is always 90 degrees.
Always. No matter where on the semicircle you pick the point.
Doesn't matter where. Pick any point on that arc, connect it to the ends of the diameter. The angle at that point is guaranteed to be a right angle.
That's actually pretty cool. So you always get a right-angle triangle inside a semicircle if you use the diameter.
Always. Which, again, is why the Pythagorean theorem pops up so much in those kinds of geometry probably shown in the material. It creates predictable right triangles.
Okay, wow. So, quick recap then. We've got the basic definition: center, radius, the boundary, circumference, inside stuff, chords, the special diameter chord, arcs, sectors, segments. And then these really neat properties.
Yeah.
Tangents, meeting the radius at 90 degrees.
Right.
And this angle in a semicircle always being 90 degrees.
Those are the absolute fundamentals, and they're the building blocks for tons more complex geometry, and you see them applied in engineering, design, physics, really everywhere.
Yeah.
So here's something to think about, maybe. Considering how these simple rules, like a line just touching the circle or a line spanning its widest part, create such perfect, predictable right angles, what other kinds of hidden structures or maybe patterns might you start noticing now in, all the round things you see every day?
That's a really interesting question to carry away. What patterns are hiding in plain sight? Okay, great stuff. And that wraps up this deep dive on circles.